So be there. So every non-empty set of positive integers contains a smallest number. We always get to assume that if you look at some set of positive integers, there has to be a small element. Why do you think we don't go negative integers? Well, what is small? So yeah, you just keep going lower and lower, right? -2 is less than or smaller than -3 is smaller than -2. If you want to do it for negatives, you could flip it around and say for every non-empty set of negative integers, it contains a largest number, for example, right? But what we're guaranteeing is that there is always a stop. There is some relationship that we can define, or if you get really deep into this order set. And it's actually going to show up in a very interesting part of hopefully today, if you get to it, if not on Wednesday, where just knowing that we have the smallest element is going to prove your integer division. If you divide two integers, there's a quotient and a remainder. Those two values are unique. But we kind of got to get up to that point first. So, other than axioms, two other main tools we have are definitions and theorems, right? Well, we like definitions because it's pretty much our tools that we get to use. Let's not go too crazy. Turn off with a nice, easy definition, nice, easy tool that we can use. We say that a non-zero integer I'm just going to use lowercase t is a divisor of an integer s. If there's an integer u such that s is equal to times u. And to show that t divides s, or t is a divisor of s, I would just denote that really quickly so we can save a lot of language. T vertical line s. Okay. Let's see how much little notation tricks you remember of mathematics, or if not, you're going to learn some. If t is not a divisor of s, how do we write this? Yeah, you just cross it out. You want to say not something, just put a nice little slash through it. So in this case, it would be t vertical line, the slash through it, and that's right. Similar as you see in set notation, where if you're wanting to say a is not an element of the set containing 1, 2, and 3, right? You just put a nice little slash through it. That theme you will see throughout all of mathematics, no matter what field you get into. Okay. Another definition when it comes to dividing is there's a special type of number that we love. They have very interesting properties. They all stem from that definition of addition. You happen to know what type of numbers I'm talking about? Special type of numbers that are defined by what can divide them. How about that? Prime numbers, right? We can also define prime numbers. So, for example, definition of prime is a positive integer greater than 1. whose only divisors are what? Yeah. So these are two main tools. We're going to see this a lot. Especially in this course, it's going to become a lot of definition, theorem, definition. But part of the reason we do this is we want to always make sure that we explicitly state out what we're working with, right? Prime is an easy example. We all know what that is defined as. Like I said, an even number, right? What would you assume I mean by an even number? Number that's visible by two, but maybe I went to a different school or I grew up in a different country where it was taught to be a little differently and even not for flipped. What we know is odds are even, what are even odds to them. So we make sure we write that all this stuff out explicitly so we all know exactly. That's not necessarily the interesting point of even this class. More interesting point, in my opinion, is actually proof writing. We get to put our logic skills test as well as how well we can articulate our arguments. And those always show up in the form of theorems. Theorems are saying if I'm given certain tools, what are the things I can do with these tools? What are the different things I can do? So let's start off with an easy one. We're going to let A, B, and C be integers. If C divides A, and C divides B, then C divides A plus B. And this makes sense. Can someone give me an example of where this works, choosing A, B, and C?
12 and 3 and 4.
Yeah, so, well, be careful. You're looking in the right area with factors, right? So I'm looking for an A and B that are both visible by something. So C, that case, right? So I could still stick with like, A is 12 and B is 4. What would C have to be then? Or what could C? 2. Could technically be 4 as well, right? Or I'm gonna, I guess it could be negative, but usually don't like to go into negatives. It's trickier with definitions. But okay, does 2 divide 12? Yeah, 2 divide 4. Well, does then 2 divide the sum of 12 plus? Yeah, right. And I could go through this and I could pick other combinations of numbers, 25 and 15, for example, right? 25 and 15 are both divided by 5. If I add 25 and 15 together, what do I get? 25 plus 15 is 40. It's 40 divisible by 5. Yeah, absolutely, right? So we can give examples, but our example is going to be the end all for this? Because how many options do I technically have? Potentially.
Okay, so I have confused with like the whole sign and stuff. So is C supposed to be larger than A and larger than B?
Go back to our definition, right? We say that a non-zero integer t is a divisor of an integer s. And how we read this, how we do notation is, this is the number that's divided into. First number gets divided into second. So we could say 2 is a divisor of 6. 5 is a divisor of 4. Yeah, glad I can clarify. Thank you for asking. So that we can give examples as kind of like a proof of concept, right? But it does work in some instances. It's not necessarily going to hold all of us. We can't show all of examples. So we have to stick to working in abstract way. Okay. This is where we start writing those proofs. And the one thing that we always have to remember is whenever we start out a proof, we need to explicitly state what are we working with, right? And that always just goes back to the statement we made, theorem. So what do I have to work with from that statement? That's that very first line.
A, B, and C be integers.
Yeah, let A, B, and C be integers. That's the first thing I notice. I get 3 integers to work. I don't know why I made it proofs plural. But what else do I get to work with here?
If C divides A and C divides B, then C divides A plus B.
You read off the statement, but you're looking in the right area, right? I have a close. So look at the if-then statement, right? Following the if is what we call our hypothesis. Following the then is the conclusion. Our goal is always, if the hypothesis is satisfied, we want to be able to determine conclusion is true. So we get to assume the hypothesis, assume the if, and then with that information, work our way down that conclusion. So what is my hypothesis here for that if statement?
C divides A and C divides A.
Divides B, but yeah.
I mean B.
All right, so you also want to let B divide A, let C divide B. And then I'm just going to write this in green. This is our note. This wouldn't necessarily be like in our final draft of this quote essay, right? But what is our goal to show? B divide, yeah, A plus B. But even though I don't know exactly what A is and exactly what B is, just knowing the fact that C divides A and C divides B, then C is going to be able to divide some. Well, think back to the definition of divide. If C divides A plus B, what does that mean?
Is able to go into itself as well?
No to both of those, but you're starting to try to think about what I had, right? So what happened with your answers, you went back to my hypothesis. But what does it mean for C to divide anything? In this case, particular A plus B. Well, it doesn't have to be smaller, it's the same as A plus B now. Right? But what did my definition say for division? T is a divisor of S if what? Some other integer that I can find such that S equal to T times C.
P times A.
Yeah, which means when I'm going down to try to prove that this number C is going to end up being a divisor of A plus B, I need to show that C is something, or sorry, A plus B is equal to C times something. That's what I need to show. So I now have my end goal in mind, my end position. Because as long as I can show A plus B is equal to something times that integer C, then I know by definition C will divide A plus B. So now that we have our end goal in mind, let's start working with some things. All I have right now are that A, B, and C are integers. And what other 2 pieces of information? So it doesn't
C
divide A
divides
plus
A.
B, that's what we're trying to do. right? But I know C divides A and C divides B. Well, what does that mean then? By definition, what? Well, so that's C divides A. And yes, you're gonna answer this still. That's what we're trying to show. You're both skipping ahead too far, right? You have to start, and that's not necessarily a bad thing. But that's what you want to do when you get comfortable with this. So we have to break down our pieces of information.
A equals.
Yeah, so there's some integer out there which we can call u, such that A is equal to u times C. So there exists two integers. We can use u. Someone else can be another integer, a label for another integer. X. So because we know C divides A and C divides B, we know there has to be some integer out there. We're going to call it u and x such that I can rewrite an A as some multiple of C and B as some multiple of C. So this is what I'm talking about, just breaking down that definition, using the definition itself. Is there anything else I can break down right now? Not really. Like maybe I could try to break down what it means to be an integer. That's not necessarily going to help me too much. So then I say, okay, well, if this is all the pieces I have to work together, then what do I need to start looking at next?
Finally, they make that. Equals B.
Yeah, right. What we kind of identified here. We want to be able to then say A plus B is some integer times that factor C. Well, usually when we're doing this the first time or two, it's not going to be perfect, right? You just kind of mess around with it. But what we are realizing is that we need to consider what does A plus B look like? Well, I have no idea about what that sum actually is. I don't know what A is, I don't know what B is. But I do know how I can represent A, how I can represent B. How can I rewrite A? Yeah, it's going to be C times U. And how can I rewrite B? Like that.
C times X.
I go, okay, well, can I work with this expression in? Well, what do both those have in common? Yeah, C. So what can I factor out from both of those?
C and you get U plus X, yeah.
And I now look at what I have. Even though it's a string of expressions through equalities, the far left-hand side, I have A plus B. And on that far right-hand side, I now have what? C times an integer. Because if I take two integers, U and X, add them together, is it still an integer? Yeah. So, well, now what can I say about C in the sum of A and B? Hmm? So since I can look at A plus B and have it be C times some integer, we get C divides the sum of A and B. What do we put at the very end of any proof?
Square box that shading in.
Yeah, so there's technically two options. If you want to be really old school, like Melissa suggested, QED. is one option. Quad, erat, demonstratum. Only remember that because I talked about it in discrete math video. So that's Latin for, what was it, to show or something to demonstrate. Essentially, you're done. Remember the Latin translation. But the more modern way of doing it is just that nice little black square at the end, saying everything that needs to be known about this has been written. You don't need to go anywhere else. There's no other arguments. Okay, so what questions do you got about this so far? Or sorry, let me ask that a different one. What questions do you have?
General concepts or rules you wish to get ahead of different something. We don't go and to create.
So it's always look at your hypothesis and assumptions, right? Those are your building blocks, your tools that you get to work with. And then you have to figure out what you can do with them, right? So when we kind of start off and through most of this course, you're not going to have too many variables or too many tools to be juggling around. But you always have to be thinking about what can I break down by definition, right? So for example, when let me scroll up a little bit. We identified we really had two working pieces, right? So we had three integers, and how those integers are related to each other. So you divide A, so you divide C. So then I have to think about, okay, can I do anything with the definition of integers? Potentially. Can I do anything with the definition of divisors? Yeah. Let's break that down and see once that's broken down what moving pieces I have. And then from there, it's a little bit of just kind of your own intuition, initiative, and intelligence to bring all the pieces together. But once you start doing enough proofs, you kind of start to find your own flow and thought process to it. The other thing I want to say is, even though I'm presenting to you one nice needed proof that's in order, your first couple times trying to figure this stuff out, it never looked like that. Unless you're really lucky where you just figure it out straight away. There's always going to be scratch work, right? Just like if you're finding a derivative calculus, you might not be able to do the first time you go off the side, figure out how you want to write it, how you want to break it apart, you know, write all your different rules, and then you bring it all back together for your final. Let's do that. Let's do another one. Let's throw in a little bit of notation here. What have I just said right there? Underneath here. So let A, B, and C be elements to be very particular, the elements of the integers, but really let them be integers. Okay. Now what we want to show is a transitive property for divisors. If A divides B and B divides C, then A divides C. So we want to prove this. First thing I need to do is state what I'm getting to work with. So what am I given as an assumption and what am I given in my hypothesis? Yeah. So I know we have three integers. And what else do we get from the hypothesis?
A divides C.
Divides B. And B divides C. And now that we've stated out what we've got to use, we're just going to make this mental note, which I'm going to be writing out in green. Our goal is to show what?
A divides C.
A divides C. So if I'm looking for A to divide C, that really means by definition, I'm looking for A to be equal to something times C. Okay. Now I just have to figure out how can I use the definitions of A divided B and B divided C to make that appear. What's not A's? C is equal to U times A. All right, so what can we break down? What definitions can we use?
We use the one that we just used.
Yeah, divisors, right? We know A divides B and B divides C, so we can break down what does that mean? Definition. So since A divides B and B divides C, there exists two integers. So give me some letters.
X, Y,
We'll do M and Y, so we can change it up a little bit. M and Y. Which let's write using that notation. So based on the definition of division, since A divides B, then I know there exists an integer such that B is equal to what? Yeah. M times A. We'll let the M go with that definition of division. What about for C? C is equal to what then? No, not Y and A,
oh,
B. Then I know B is some multiple of A and C is some multiple of B. See some thoughts going on. What do we do from here? What's my goal? What am I trying to end up with?
We're trying to end up to see, show that A divides C.
Yeah, so A divides C, but what's another way that we could write to show that A divides?
C equals zero.
C is equal to some integer times A. Well, so far, yeah, yeah, exactly. I know because B divides C, C is equal to some integer times B. But then I also know how I can rewrite B itself. It is some integer times A. And I just look at that expression and go, okay, is this what I'm looking for? Is this actually some integer times A? Is showing C is just some integer times A? Well, yeah. I regroup that multiplication, use my associative property. This is the same thing as Y times M times A. Well, Y is an integer and M is an integer, and we know innately, you multiply any two integers, what do you get? An integer. So through this string of expressions, what have we now shown? C is equal to what? Some integer times A. Well, since I can write C as some integer times A, what does that imply by definition? Let's see. Since C is equal to some integer A, then we know A divides C. Now, if I prove what I set out to prove, Then what do I put at the end of it? For us, we're gonna go with the square. If you do QED, you're more than welcome to do that. What questions do I got? Always breaking down the blocks that you have and figuring out how to rearrange them. It's not always as simple or as straightforward as some of these groups can be, but once you get comfortable with them, they'll start to see. So I promise you to talk about integer division by the end of the day. We're not going to get to prove it. We're going to get to actually prove it on Wednesday. But one of the most important theorems, and it actually becomes I know Melissa mentioned cryptography. This theorem is actually the basis for most cryptography because it develops what we call modular arithmetic. Familiar with modular arithmetic, which we'll deal with a little bit in this class. But the division algorithm I always love coming back to. This is what, for me in the state of North Carolina, I learned this in 3rd or 4th grade. The 3rd or 4th grade concept, I'll just say elementary school concept. And when you divide two integers, there's always a quotient remaining. So the division algorithm states, let A and B be integers with B greater than 0. Then there's going to exist unique integers Q and R. Such that A is equal to B times Q plus R. Where the value of R has to be greater than or equal to 0, but strictly less than B. That seems familiar now? So this proof is actually going to be a little bit more involved. This is not necessarily something I would expect you to come up with on your own, but it would definitely be something that once you've seen these styles of proofs done, you're then going to have a new trick that you have in your repertoire that you can apply to other scenarios. And this proof is going to rely on that well-ordering principle. The biggest thing, the biggest piece of information that we're going to need to know is that a set of positive integers has a smallest element. But when you break down the proof, we got two parts here that we actually have to do. Anyone know what the two parts are? This is at the conceptual level.
With the division algorithm?
Yeah, what division algorithm?
Are you talking about the thing where we can reverse it, like you are or something like
No, but I think you're getting into contrapositive, kind of like where you flip your perspective on the problem and work with that. That's definitely a way you can prove things. This is very niche, and I wouldn't be surprised if you've never heard it stated this way before. I would just ask to see if maybe someone has. So let's follow the then statement, right? So let A and B be integers with B greater than 0, then what? Whoops, I said then, should be then there. then there what? Exists unique. There are two things we have to do here in this proof. We have to show, one, Q and R exist. And then not only once we know they exist, what else do we have to show? That they're unique. But this is what we call existence uniqueness proof. And which means we have split this into two parts. After this, I promise will be done. I see the time. We have to do two things. One, is knowing just that A and B are integers with B greater than 0, that I can find such a Q and R. So A is equal to B times Q plus R. And then, once I have the existence of such numbers, the Q and R, show that they are the only one. There's not multiple options for me to choose. Okay. So on Wednesday, we're going to break that down. We're again going to see how all we need is the well ordering principle to actually prove this. So I'm going to stop there. If you have any questions for me, feel free to stick around after class and ask. Shanika, look for an email from me, please, after this. Okay.
Say that again.
Look out for an email from me after
Okay,
this class.
okay.
And I'll make sure to get this recording up as soon as possible. Yeah, if you got no questions for me, then feel free to get on out of here.
All right, have a good one.